time-ordered correlators, advantage and application. Tom, take it away.
Oh, thank you very much for the thank you very much for the introduction. So I'd like to present some results from our team that came out last year on out-of-time autocorrelators and tell you a little bit about our claims for quantum advantage in measuring out-of-time autocorrelators on our devices, and also some applications we think these might have in assisting nuclear magnetic resonance spectroscopy. Before I move on, I'd like to acknowledge the team of people that went into this research. This is the Quantum AI team. Actually, this photo is about 3 years old now. We've grown significantly since then. It takes quite a large group of people these days to build, maintain, and run a quantum computer. This has grown so large. Like I think when I started in this field, a state-of-the-art quantum computing lab required like 10 to 20 people, but we've easily gone well beyond 10x that. I also want to thank, the results I present on the NMR section, this was a significant collaboration with a lot of academics. So this is especially like the group of Ashok Ajoy from Berkeley, some of our collaborators from Google DeepMind, which assisted in the circuit simulation, and collaborators from QSimulate, which helped us with our classical chemistry. Now, I understand that this is most of you are physicists by trade. I assume that everyone here has kind of like heard a little bit about what a quantum computer is, but at the same time, everyone likes being told what they already know, so I like to kind of start off with something that start off some slides to keep everyone on the same page. So at Google in Quantum AI we study quantum computation. And this is the idea that if I replace the unit of information in my computer with if I replace the standard bit in a classical computer that undergoes the laws of classical mechanics with a qubit that undergoes the laws of quantum mechanics, I can have an exponential increase in the number of numbers that I would need to describe a single state, right? Which is just a statement that a quantum state on n qubits has 2 to the n components, or 2 to the n minus 1 free values, so minus 1 for normalization. Whereas, compare that to n bits, which I can describe with n single bits. And so this is an exponential improvement in data storage. It pretends to like an exponential improvement in computation. This is not a proof. That took, I think it was about 10 years going from first thinking about quantum computers to showing, like an application where Shor's algorithm, where we, to this day, believe that there is an exponential quantum advantage. And we're kind of keen on, and because we expect that trading classical bits for quantum bits has an exponential quantum advantage in solving certain classes of problems, this has spurred a lot of interest in the last decade in actually building one of these devices, getting them to work, and getting them to scale up. Okay, so there are many different types of qubits. I think this is kind of, quantum computing is at the Betamax versus VHS stage, if you're old enough to remember what that means. We're not like, we haven't yet settled on a platform or a technology to use. And I want to acknowledge that other technologies exist. Some people in the world like to build their qubits out of the spins of electrons, like sitting in, say, quantum dots. Other people like to build their qubits. A qubit can be any two-level system, really, right? So you can take, say, the hyperfine levels or the electronic states of an atom, if it's whether it's a neutral atom in an optical lattice or a charged atom in an ion trap. Other people like to build their qubits out of photons, but at Google we like to build our qubits out of artificial atoms or superconducting circuits, which are these things on the right here. And we get a lot of those and package them. It's a very similar process to, like to classical chip, the computer chip design, except that we're using superconducting materials instead of regular semiconductors. You wind up with a package like this qubit on the right. And this is a photo up here on the top right of our latest chip to come out, or our latest chip architecture, which is called the Willow. This is basically the spec sheet, just to give you an idea of how well we're doing right now. We have about 100 qubits. They're always arranged in a square lattice. And depending on what type of gate you want to apply, we have error rates, which is currently the bottleneck for errors in a quantum computer is given mostly by this 2-qubit gate error. This kind of dictates how large a circuit you can run before the entire thing decays. We're sitting at about 0.33% for a CZ or 0.14% for an ISWAP-like. This data sheet actually came out. This is the data sheet from when we released Willow. Part of these numbers are control errors, so these things have improved since then. On most other metrics, superconducting qubits are competitive with or better than the state of the art other contenders. I think the one thing that we have that we definitely improve over many other devices, which is going to be necessary for some of the results that I show you today, is that our qubits are incredibly fast. We can measure, sometimes up to 1 million or like 100,000 to 1 million, taking 100,000 data points per second, which is significantly larger than, say, ion traps or cold atoms. Not many did this on those other platforms, but it is an advantage that we have. So this is where we're sitting. And the reason why I said that the 2-qubit gate error is a really important feature, at least it is for the stuff we have today, is because it's so far away from what we need. Okay, so if you look at like the practical applications that people have proposed, the killer application of quantum computing possibly being quantum chemistry, nitrogenase, although recent advances have maybe solved this without a quantum computer. Most of these applications, or most of the quantum algorithms, when you compile them down to the level of individual gates, you need to execute at somewhere between 1 billion or more gates, right? It's like kind of between 1 billion and maybe even up to 10 to the 12 or more quantum gates in a single computation. And there's a nice rule here that if I need to execute n gates, the error rate that I need to have per gate is around about 1 over n. Okay, if I need to execute 1 billion gates, I better have an error rate per gate of about 10 to the minus 9. And this is basically because your circuit fidelity decreases exponentially in the number of gates. Okay, and so actually if I have 10 to the 9 gates and I have a gate error rate of 10 to the minus 9, then my fidelity will be roughly 1 over e. It's a nice feature of that. And this exponential decay, having a fidelity of 1 over e is probably something that we can tolerate in an experiment or in a computation if we know about it and we design our algorithms appropriately. But this thing decreases quite quickly. If you have, if I have an error rate of 10 to the minus 9 and I'm doing 10 to the 9 gates, then I have a fidelity of 1 over e. But if I'm doing twice as many gates, my fidelity drops to 10%. If I do 4 times as many gates, my fidelity drops to 1%, and very quickly I go out the back door, and there's no way I can ever record a signal. Now, there is a solution to this. If we don't expect, every time I ask the experiment, I go to the experimentalists and I say, oh, it's simple. You just have to increase your physical qubit fidelity by a factor of 1 million. They laugh at me. But the solution is quantum error correction, and this lovely theory that if I can encode one logical qubit across many physical qubits, such that this redundant encoding can be used to detect and correct errors as they occur. Here's the results from our team from last year, where we actually demonstrated this. I mean, in 2023, we demonstrated error correction kind of at the threshold of the surface code, right? And the idea here is that you're using this large lattice of qubits, of physical qubits, to encode one logical qubit, and you're measuring the decay rate of that qubit. And quantum error correction says that as I increase resources I'm using for my encoding, the logical error rate will decrease exponentially. And you can see this in as much as, fitting a line through 3 points in an exponential curve is indicative of an exponential decay. The theory definitely predicts this, and we are, we think that we're well on our way towards, building a fault-tolerant quantum computer. So this is kind of where we are then, or this is where that recent result puts us. We're currently seated there. With that recent result, we achieved what we called milestone 2. We demonstrated that the quantum error correction works. The next milestone that we want to achieve is milestone 3, which is a long-lived logical qubit. So this is a qubit that is able to do, say, 1 million operations before it decays, right? Or another way of thinking about this is, it's a qubit that starts to be like a superconducting qubit that starts to actually be alive on times that a human being can understand. Should be quite cool. And then after that, we have kind of, like a number of step ups as we increase basically increase the number of qubits by, factors of 10 every single time, all the way to, this milestone 6. And this is currently the point where, we have provable applications or algorithms that have been costed out to the level of, your underlying physical qubits that we can run, that we think this is at the point where where quantum computing will achieve its, Feynman stream. And then, this kind of sits us in this position, right? We're currently in what John Preskill coined the NISQ era, right? Where we really, the dominant issue that we face is noise, is this 2-qubit gate error rates. We can see in the distance this fully fault tolerant era where we're no longer limited by error rates, and the only thing we care about is making our circuits take the shortest time possible, and we can afford to use additional logical qubits. In the middle, something that we're kind of getting very interested in, and something that I think quantum computing research will be, really pushing to in the next 5 years or so, is this idea of early fault tolerance. As we kind of hit milestone 3 and go up towards 1,000, 10,000 qubits, we'll be able to start doing limited amounts of error correction. We won't be able to yet kind of achieve the logical error rates of 10 to the minus 13, but maybe there are kind of still interesting quantum applications that we can achieve there. And this is kind of really important because to date, no one has demonstrated what we're calling, quantum benefit, or IBM would call quantum utility. And this is because if you want to think, there's been many experiments. The number of papers that people have run on our quantum devices and others numbers easily in the thousands now. But to date, you have to take these algorithms and put them on 2 scales, right? You think about the difficulty of the algorithm, and you think about the usefulness of the algorithm. And there have been many interesting cases where people have run quantum algorithms that, if they could scale them to beyond classical system sizes, they would be of use, right? So chemistry simulations or machine learning, right? All of these are problems with real applications that people keep coming to us, day in, day out, and asking us to solve. And we have to say, we can't do it yet. Our error rates are too high. And then on the other side, random circuit sampling is the example of a problem that we could easily do beyond classical. I think our current state of the art estimates are that to spoof our quantum computer, you'd require about 10 to the 11 years on a classical device. However, the promised land lies in this space where usefulness and difficulty intersect, and to date, no one has managed to achieve that. And what I'm going to talk about today is our attempt to kind of get a little bit closer with 2 different papers that are very linked, right? The first one is a paper where we've demonstrated verifiable quantum advantage. So this is verifiable. It is not yet useful, I would argue, just because we haven't yet found a use for OTOX in random circuits. But the very nature, if your quantum algorithm is not verifiable, if I can't even check that it's correct, if I could replace it with completely random noise and you couldn't tell the difference, and how can you ever hope that it would be useful? So this is, you have to get to verifiable before you get to useful. And the second thing that we've done is to find a practical application in NMR, right? And that we can tie to the verifiable quantum advantage, because they're both using out-of-time autocorrelators. And so, although I don't want to claim that either of these 2 are achieving, beyond classical quantum benefit, I want to take this as a pretty big milestone to reach. Hopefully, the fact that there's a line between these 2 allows us to show that we could, possibly cross here and find something useful that's also beyond classical.
All right, Scott, question.
Yeah, please.
Previous slide. So if I gave you a fully fault tolerant quantum computer with many logical qubits, are there any applications, protocols, or algorithms that you could implement that would allow me to fill that empty quadrant?
Yes, absolutely. So definitely we have scoped out. Our team has scoped out, for instance, applications in quantum chemistry. So, I mean, nitrogenase is now one that's up for question, but definitely there's P450 enzyme. There is some work looking at materials. So looking at ground states of strongly correlated materials, and other work, say, there is another paper that's been costed out to the level of quantum error correction on the ruthenium-2 complex. This is Marcus Ryer's work with Microsoft. So there are applications. I would say then there's also the looming thing in the background, which is Shor's algorithm, which I think now current estimates are that is less than 1 million qubits to run at like RSA 2048. But honestly, I'm not that interested in trying to break the internet. I'm much more interested in quantum simulation, algorithms. So I will say, what I've just mentioned, that is the set of applications. I'm like, if you gave this to me tomorrow, I would be able to get you a circuit, by that time to run on this new quantum computer that you've given me, right? But that's a very small list. And so one of the things that I will flag here, and this is actually something, that our team has funded, and there's an X Prize that we funded in collaboration with GEDSTA, the Geneva Science Incubator, to try to improve this situation, is that actually quantum application research is lagging, right? That like right now, I can give you many rough ideas of like, high energy physics or high temperature superconductivity, or looking at inertial confinement fusion, or looking for new battery materials. I can give you like rough ideas of what those things might be, and I can tell you kind of rough ideas of quantum algorithms, which in an abstract setting, like I know that you will, with that some of these problem instances will be BQP hard, right? Kind of like you can easily find instances of problems that are like, or problem sets that are BQP complete. But then there are two stages in this is a perspective piece that came out from our team at the end of last year. I really it's like the 5 stages of application development. And there are 2 stages that are kind of missing. The first one is actually kind of going from instances that are that are BQP complete worst case to typical case problems, right? So kind of like, here is a problem instance where like, if I just hand you a random problem drawn from this example, a quantum computer can solve that problem, but a classical computer cannot, right? And that's like actually identifying instances of this is still quite hard. And what I'm going to present today is one of the few instances that we actually think is a bona fide and relatively well proven instance of typical quantum advantage. And then stage 3 is to go from like, some people just skip stage 2, they try to go straight to stage 3, is to actually like find real world applications and like find, say, a problem in chemistry or a problem in material science with established quantum advantage of, hey, if you can calculate this is a property that we absolutely cannot solve on a classical computer. And obviously this is kind of a bit hard as well, just because suddenly, any paper that you write is a target for people to attack. I mean, it's a target, you've said, hey, it's a problem that classical computers can't solve. So that makes people like the classical computing experts really want to solve that problem. So obviously there's always some kind of lifetime on this, but definitely like the number of real world applications with established quantum advantage is smaller than we would like at this point, that I would say, and especially applications in simulation. So for the rest of this talk, I'm going to go over, kind of our attempt to improve both of these. So on the left-hand side, here is an instance of a set of problems I believe is typically hard to calculate, which is instances of OTOC squared on random circuits. And on the right-hand side, this is an application of this, to actually learn parameters or like learn structural features in molecules using NMR spectroscopy. Okay. So let me start off, trying to motivate, like how would we try to like search for a problem with quantum advantage? And I think it's important to, to say 2 things, right? We talked about, I think our team had this random circuit sampling experiment and claimed that we have a beyond classical experiment. This was done back in 2019, right? Now, the random circuit sampling is nice, but it's not verifiable. You cannot check that you have done random circuit sampling correctly unless you have not just access to a large quantum computer, but you need to actually simulate the system classically. You don't get a quantum advantage, or you can't you cannot check that the output of a random circuit sampler is correct without a classical computer sitting there to test it. This means it's kind of a bit of a useless benchmark. It's a nice benchmark, but it's not a great benchmark. Verifiable and verifiability is something that I can check if I have access to, say, another quantum computer, or ideally, if I was, say, simulating a system in nature, I could go and actually run the experiment and check it, right? So it doesn't have to be simulated. We're loosening the condition. Verifiable in the CS language often means like verifiable on a classical computer. so a problem that say sits within NP, we're loosening this. Even if you just have another quantum computer, you can check that our answer is correct. And so the obvious thing here is to look at something like an expectation value, right? Where you run a circuit, measure a number at the end. This has a bit of a problem. This has a couple of problems though, and this is it's surprising. Like, to measure an expectation value has much more stringent constraints on your device error than random circuit sampling. And the reason for this is that the random circuit sampling problem could tolerate fidelities of about 0.1%. But measuring an expectation value, suddenly classical computers are a lot better than this. And so to go beyond classical to actually achieve quantum advantage, we need to start measuring expectation values with error of about 0.1%. And we also need to make sure that the expectation values don't converge to something, right? So say, for instance, if I just take a random circuit and I take a computational basis state and I evolve it under a random circuit for like log depth, and then I measure an expectation value of that random circuit at the end. I can tell you immediately, I don't need a classical computer or a quantum computer to tell you what the output of that expectation value is going to be, right? It's going to be 0 because expectation values in random circuits concentrate, right? So it's 0, like up to exponentially small wiggles. I can't measure those exponentially small wiggles in a quantum computer, so I can't claim quantum advantage. And so we need to have something which has some sensitivity to microscopic details to prevent guessing. And we want to have like many instances, right? Like, I don't just want to have, say, like one instance of a Hamiltonian that I can simulate and get something out. I want to be able to like keep handing you problems, right? Keep handing you problems and be able to say, if you can solve this one and this one and this one and this one, then you can claim advantage, right? So we want to have some kind of randomness in here that we can draw from. And the solution that we've found is to look at out-of-time autocorrelators in random circuits. Okay. Now, I can actually see you all right now. So can I get a hands up? Who knows what an out-of-time autocorrelator is? Okay, good. Then you probably know more than me, so I don't have to go into this in too much detail. But just again, the key point is an out-of-time autocorrelator takes this form here, where I have a butterfly operator and a measurement operator, and I'm going to evolve the butterfly operator to time t, right? So this evolves into the Hamiltonian, and then but then I sandwich it between two measurement operators that are at time 0, and this is why it's out-of-time ordered. And this has a nice feature when B and M are spatially separated. So B is like kind of down here on my circuit, and M is all the way far away. Actually, this B should probably be down there, but whatever. And the idea there is that this B operator propagates, like the action of U on it, propagates it as a front, right? As time increases, or in this case, like as I add more cycles to my circuit, right? The butterfly operator kind of spreads in space. And until it actually spreads in space enough till it touches M, this C of t is equal to 1, right? As you can see here, this is kind of like a measure of OTOX. So this curve here is like a measure of OTOX as I put my measurement qubit further and further away. And you can just see that like the decay takes a long time to set in. But if I let time go out to infinity for an ergodic system, this thing will just decay to 0. And so eventually, all of these curves kind of drop down to 0. And the cool thing is that in this bit in between, when your measurement qubit is sitting within the front of the butterfly operator, you are actually sensitive. This front is somewhat chaotic. It's actually sensitive to microscopic details of the circuits and of the gates in the circuit. Okay, and the sensitivity in microscopic details, this gives us an ensemble that we can sample from, and that ensemble is just draw these single qubit gates at random, right, with a fixed 2 qubit gate position. Okay, and you can check here on the right is like looking at how the standard deviation, what is the standard deviation of my my OTOC as a function of as a function of like the number of cycles in the problem. And you can see that this standard deviation stays quite large. Here I'm kind of like moving the measurement operator back every time. So I'm kind of like increasing the problem size rather than increasing time. And you can see that the OTOC stays quite large and saturates, whereas something like a time autocorrelator will decrease exponentially. Okay, so this is like this is something that you expect from physics, but it's good to check it in the system. So once we've done this, okay, we have a signal, and I have a problem that like in principle you need to simulate the dynamics. You need to simulate the dynamics of an interacting random quantum circuit, which sounds quite hard. So this is looking like it's a pretty good contender for a claim of quantum advantage. The next step, if you actually want to claim quantum advantage, is to turn around and say is just to say, okay, we can't really prove that this can't be simulated classically. The only thing that we can do is we can go and beat our heads against it for a long time and take a crack team of physicists and try to simulate this classically, right? Like generate a bunch of data on our circuit, and then send it to what we call a red team and say, hey guys, we think you can't do this, prove us wrong. And they did. So the first so the first thing that we've got here is actually a slightly negative result, or it's a positive result if you're a classical person. It's a way of simulating an OTOC in a random circuit in this in the random circuits that we're interested in. And it's interesting because we can simulate this OTOC despite the fact that the OTOC is giving fluctuations. Sorry. Now, let me go briefly through how to do this. So the way you do this is that you work in the Feynman path integral formalism. Okay. So the idea about the Feynman path integral formalism for a circuit, right, is that what I do is I look at my operator. So I'm looking at my butterfly operator. And what you can do, you can expand this out in terms of Pauli strings, right? So this thing is a linear combination over the set of all the Paulis multiplied by some real coefficient. But you can actually go further than that, right? So going to the path integral formalism means that I don't just take one Pauli for every single point in space, but I take one, but I allow those Paulis to kind of like remember their history, right? So I kind of imagine now I'm taking a string of Paulis where at every single step between every single gate, I'm kind of like allowing, I'm recording like, oh, my Pauli evolved to some other Pauli operator. I apply the next gate, this evolves it again, okay? You can kind of see this is my best effort at a pictorial representation, right? Here's a quantum circuit up the top. If we start with like an EPS operator on this qubit down here, this might evolve, and then it will evolve again. And then when I apply this second gate, this X could evolve to a Y and a Z, right? And you can evolve this thing on. And every time that you have some non-Clifford gate, this evolution is not like complete, right? You evolve, you have like a fork, your wave function, like your wave function generates multiple paths, right? And these guys will expand out. And the key, the reason why you get quantum dynamics here is because these paths might expand out, but later on they can kind of come back and join again, right? And you can get a feature which we call loops, right? And a loop is where basically, I have some Pauli operator, two sets of Pauli operators that split at some gate, and they recombine later on and interfere with each other, okay? And this is kind of you can do exactly the same thing if you just take a state and you represent it in like a Markov formalism and do like classical Monte Carlo on your operator instead of treating it under like unitary evolution, right? The two things are identical. And here we're just doing this in the operator basis. And the reason why we're doing this in the operator basis is because in the operator basis, it's kind of the natural thing to treat an OTOC because you're looking at how like an operator, you're really measuring how an operator propagates through the system rather than a single state, okay? All right, so that's like this Pauli pathing formalism, which just gives me another way of writing my butterfly operator. And I can write down my, so I can write down my my OTOC in this Pauli pathing formalism. And so what I have here now is I have, it's now sum over pairs of strings, right? Because I had 2 copies of my butterfly and my OTOC. It's a sum over pairs of strings, and then you have the amplitude of each string. And then at the end now, these B alphas and B betas have been pulled out of the trace. And now I have this trace here, which is equal to like rho times m times this is a Pauli times m times this is Pauli beta t. Now, I'm going to tell you, you're just going to have to suspend disbelief and believe this, that this rho, basically the effect of having this rho here compared to it being the identity is very, very small, okay? So really like OTOCs sit in these 1D chains with random quantum circuits. Infinite temperature OTOCs and finite temperature OTOCs basically always have like the fluctuations on here are smaller than the fluctuations between you get from changing your gates. And so this means I can say replace this rho by the identity. And then if I replace this rho by the identity, I have a pair of, like basically I have this set of Pauli operators, right? Like P alpha, M, P beta. I can either commute or anti-commute M through P alpha T. And then because it's a Pauli operator, it's going to square to the identity, right? And so that means that this, when rho is equal to the identity, the only contributions to this trace come from Pauli operators, like strings of these Pauli operator strings that meet at the far end. Okay. So this is kind of a nice feature. This allows me to, like, I kill off almost all of the off diagonal elements of this matrix. And then you kind of realize, you notice something, which is that if I actually kill off all the off diagonal, like all of the off diagonal terms, so like if I say fix this B alpha to be equal to B beta, sorry, if I fix alpha equal beta, so I don't just assume that, like, I kind of assume that Pauli strings that, not just Pauli strings that don't meet at the ends are killed by the trace, but kind of Pauli strings that don't meet, that differ at any point along the path. If I assume that all of those are killed by the trace, then I wind up with this function here, and this has two nice properties. So the first property, which I haven't told you, but you can maybe see, is that this B alpha squared is actually a probability distribution. Not only is it a probability distribution, it's just kind of because your path amplitudes are square normalized, right? Not only is this a probability distribution, but it is efficient to classically sample. Okay, and the way you sample from this B alpha is, I mentioned on the previous slide, right? My Pauli, I'm generating these. You can generate these paths just like going from left to right, and at every single point, you can just sample from the probability to go from, like, to evolve from one Pauli string to another Pauli string, and that will actually give you this B of alpha. Okay, if you don't follow the math here, you can read it in detail in the paper. So that's a nice feature. And so that means that this guy, the CMC, this is classically simulable. And this C of T is the thing that we're targeting. And so if this is a good approximation to C of T, then we're not in good shape, right? Then classically you can actually simulate these OTOPs. The next thing you can find out, which is quite cool, is this is a lovely trick from Philipp Suchland and Tommy Schuster. It was to note that I can generate this Monte Carlo thing by taking my OTOC, and what I do is I replace my unitary by this thing I've called U-Pauli, right? And to generate U-Pauli, what I do is in between each layer of gates, I insert randomly chosen Pauli operators, I, X, Y, and Z. Now I do this in the unitary level. I don't do it in the OTOC. So remember that this unitary appears twice in my OTOC. I do a correlated insertion. I have both the Pauli and U and the Pauli and U dagger. Otherwise, this would look kind of similar to local depolarizing noise, which destroys your signal. But if you do this random Pauli insertion and then you average over sets of Paulis, then you'll find out that you actually generate this Monte Carlo Clifford thing in your quantum circuit. This is really nice in order to actually, like, to error mitigate your OTOCs, because it gives you a really good reference signal. But it also means, and it also allows us to actually, like, probe this on the device, okay? And so what you can do is you insert these Paulis, and you try to see, like, if I insert these Paulis, do I see, like, that my signal correlation gets that my signal stays well correlated to, like, to CMC, stay close to C of T. And we find in practice that you can play around with this scheme and generate Monte Carlo, like a Monte Carlo approximation to my OTOC that is too small for comfort. That we think this is an approach that will effectively classically simulate these OTOCs. And so this took us about, I would say, a year of beating against this, only to find out that yes, we can efficiently classically simulate these OTOCs. And then we said, okay, then we have to go into something else. And there's something else that we went on to was to look at higher order OTOCs. Okay. And so if I just go back really quickly to tell you what a higher order OTOC is, you can see here, here's the circuit for running in just a regular OTOC. And if I just repeat this circuit k times instead of just doing it once, that's what I mean by a higher order OTOC. Okay. And we did that. So, and this was data taken by Zhao and Amir. I want to claim that on this slide, I think you're seeing something on the order of like 10 to 20% of all of the quantum circuit shots that have ever been taken worldwide. This was something on the order of 250 billion circuit repetitions. It was a very, very challenging thing to run. And this is in part because you can see the signal that we're trying to measure in order to claim beyond classical was very small. right? This is after error mitigation. It was about 10 to the minus 2. Okay. However, we've gotten two claims for quantum advantage that have not yet been simulated at the same cost as on the quantum computer. The first one is to actually do an OTOC. This is an OTOC on a 95 qubit grid using about 1,000 gates. The best competition for this is the Monte Carlo algorithm that I just described. It takes about the same time as exact simulation, which is about 72 hours per circuit. Okay, so by comparison, this took us about, I think, a couple of minutes to run on the device. So there's still quantum advantage here, but the difference between 72 hours and a couple of minutes isn't that large. We expect this number to be brought down. On the other hand, here is our big claim for quantum advantage is this OTOC squared. So this is where you run 4 copies of, so you do U butterfly, U dagger, U measurement, U butterfly, U dagger, and then you measure the thing out. Okay. This is on 65 qubits. I think it's got about 700 gates or so, if I remember rightly. You can kind of see the layout here with the measurement qubit and the butterflies up there. And the exact simulation of this circuit takes about, our best estimates are that it will take you about 10,000 hours. I should say, this is exact simulation on Frontier, the world's now second largest supercomputer. So this is 10 to the 4 hours on Frontier to simulate any one of these points and check that we're correct. There is a heuristic method that we think may reduce this number, which is you can basically cut gates out of this circuit and make it smaller and smaller. We haven't found a way of doing that that's not like a complete heuristic. So we don't have good estimates for how much this will reduce the exact simulation cost, but we don't think it will take it beyond. We think this quantum advantage claim will, we think we have enough space here that this quantum advantage claim will hold. Any questions about this before I move on to applications and away from physics?
Maybe just to clarify. So you said the exact simulation time is 10 to the 4 hours per circuit, but is it true that you're simulating the exact circuit, right? But on your quantum computer, you're running a very noisy circuit, right? And if you're doing OTOC like square, OTOC high power, you'll have like higher and higher noises coming. Is there a point where noise will overwhelm your advantage claim?
That's a really good question. So when I say exact, I should be careful. When I say exact simulation here, what I should actually mean is to get within the same error bars as what we got, right?
I see.
So that is doing a tensor network simulation, but then you're truncating your bond dimension a little bit so that you can, you deal with that.
I see. So your truncated tensor network produces your truncation inside tensor network, for example, will produce errors too, and you're basically matching the error rate of a quantum computer.
Exactly.
I see.
Yeah. You can see the details of this are in the appendix. This is a very large amount of work from Salvatore Mandra, who is like, I think that there's a fair amount of work that had to go into developing new contraction pathway codes for this and basically running new running sat solvers on top of this until we could find the best contraction path. And then you need to balance out kind of different sources of error between taking some approximations with the choice of initial state and also doing truncating your bond dimension so that you keep this at a reasonable level. There's one of the challenges that we have here in putting this estimate down is obviously we did not go and run this. Right, this is the best estimate that we can make is 10 to the 4 hours on Frontier using a model of the nodes of Frontier that we got from NVIDIA. So I think I believe that it's as a conservative estimate as possible. Kind of like whenever we have any doubt over something, we always are on the side that the classical computer will be faster. But it is pretty well thought out, I think.
I see.
But that's a really good question. Yeah. Anything else?
Maybe a sort of different direction, but so obviously you mentioned maybe in the earlier part of the talk that there's a necessity for a efficient kind of verification scheme for a quantum advantage claim. It doesn't necessarily need to be there, but I think it's good if we have this classical verifiability, right? But so what is kind of a classical verifier that we can have for, you know, OTOP square or like higher OTOPs? For example, do you have any example in this specific experiment that you've done in your group?
Yeah, so I want to clarify that when so these are not these circuits will not be classically verifiable. We don't think that this is a problem that falls within NP. I would say that to the best of my knowledge, like there is a lot of work of people trying to build classically verifiable quantum, quantum algorithms, but they are currently sitting at significantly more gates than what we can actually do.
Yeah.
But I guess the best classical verification that we have for this being correct is actually kind of comes from using this classical simulation method. So because I can check my OTOX by like inserting random Paulis, right? So if I insert random Paulis into my OTOX circuit, I generate this Paul like this effective circuit, like sorry, if I insert the Paulis, I generate like these yellow stars, right? And I can confirm that against the Monte Carlo. So we can check the best I can, like, and that's not like a rigorous check of like that a computer scientist would accept. But as a physicist, if you're going to say like, you know, what's the proof that I have that my experiment is actually like doing what I'm saying and not just producing garbage, I think this is a pretty good test to say, hey, you know, like our experiment, when I average it over Pauli's, and I, you know, actually generate this Monte Carlo result that I can generate classically, I can actually like check that against the real classical simulation and they match. So yeah, that's the best I can do for classical verifiability. There's a significant amount of work that we did in basically, you know, checking this against smaller, like one of the questions that we got, you know, especially from referees was like, you know, how can we actually trust our error bars? This was work from Kostya Kachadze and I think Philippe Suchland, who basically went and, you know, like took a bunch of data from smaller system sizes where we could get the exact solution, built a model for the noise, and extrapolated this very carefully out to 65 qubits so that we could actually get the best error bars that we could here. So, you know, there's been a fair amount of work in the statistical analysis of this project. But, you know, yeah, like we cannot verify this in the same way that would satisfy a computer scientist. Very good question.
Okay, cool. Thank you.
Yeah. All right. Let me switch then to the application side, which I think was actually the thing I was asked to talk about. But yeah, let's go from problem application. So, you know, we want to turn these OTOX into, you know, from like just a random circuit thing to doing something useful. And basically the thing that we want to do is we want to kind of like, you know, as you distort a problem, as you change from like something that you know is hard to something that becomes easy, you run the risk of like making it kind of, you know, like more classically easy to do as well as you go like further into kind of more derivative problems. So we wanted to find something that was kind of like as close as possible to the system. And the first suggestion that we've had is to learn parameters from data. Okay. And so this is actually something that we did in the Nature paper. This was Amir's, this is work from Amir Karamlal, who basically, you know, you take this OTOX squared circuit. I do it on a slightly smaller system so that I don't have to take as many shots. I have a slightly larger signal. So there's, I think, 40 qubits or so. So maybe 36. And then what you do is you take, you know, you say, okay, I'm going to have I-swap gates on every single qubit, except one of these pairs of qubits, I'm going to change the 2-qubit gate. So instead of it just doing an I-swap, it does an I-swap with some phase on top. Okay, so you're like inserting kind of a Z phase in here. And then you're applying this kind of like at every single layer of your unitary. And then you say, okay, cool, if I distort this psi parameter, can I get a measurable signal in my OTOX squared, right? And you can get this, right? Like you can see fluctuations here as we change this psi parameter. And because we get fluctuations, this means that we can play a game of saying, hey, what if I just took this data? So I take 3 values of OTOX squared, which you can see like the 3 blue dashed lines. And then I hand you the system and I throw away this psi, and I ask you if you can relearn this. Okay. And you can see you can build a cost function in this. You can learn this parameter and you can say, hey, you know, like, cool, I can get this. Now, this isn't so useful for a quantum computer because we have far better ways of tomographing the system. But we think that there may be applications for this in nuclear magnetic resonance spectroscopy. Okay, and so this is coming into the second part of the paper. Now, hands up, who knows much about NMR? A couple of people could. Okay. Sorry? Well, yeah. So the point is that, you know, we're thinking about solid state nuclear magnetic resonance spectroscopy, right? And so for solid state nuclear magnetic resonance spectroscopy, a Hamiltonian contains 3 terms, although I'm going to ignore the third term because it's actually quite small, okay? And the key thing is you have a background magnetic field and you have a dipolar coupling. And this dipolar coupling is nice because this contains an inverse cube dependence on the distance between pairs of spins. Okay, so this Dij actually directly encodes the geometry of my problem, right? But the dipolar coupling is actually kind of a problem, and that's because it's you know, this generates strong correlations, right? This Hamiltonian here is quantum chaotic, or this term here is quantum chaotic. It gets in the way of taking the nice spectra that NMR that in the solution state NMR spectroscopists are used to using, right, which is a thing generated mostly by this background magnetic field and these chemical shifts. Okay, and so, you know, and this is because although the Dijs are much smaller than the absolute values of the background magnetic field, they're on par with the chemical shift, the difference between the 2 terms. Okay, so when you're in the solid state, you have, if you ever look at the spectra from NMR, you'll see you can always distinguish between spectra in the solution state, which has lovely clear peaks corresponding to individual H terms, and solid state NMR spectra, which are usually, you know, like a mess, right? These in principle, these spectra are quite often like relaxed to something similar to the Wigner semicircle law. But yeah, people try to do stuff with this, right? I mean, the fact that the Dijs directly encode molecular geometry is actually kind of a very nice probe. It's one of the few terms in Hamiltonian that really has a direct dependence on the geometry of a system. And so the current state of the art is to do the following: you take your sample in your spectrometer, and you also put it inside an ultracentrifuge, and you spin this thing really, really fast at what's known as a magic angle, and this actually destroys all of your dipolar couplings. And then if you apply pulse sequence at the appropriate frequency to kind of like counter drive the centrifuge at a specific, and you're targeting like a specific frequency between, you know, like you're targeting kind of a specific pair of carbon atoms, or say a specific pair of fluorine atoms that you've put into the system, then you can recouple these two, and you can measure, you know, you can measure basically excitation transport from one spin to the other. And this allows you to measure something up to about like 15 angstroms or so in protein systems, okay, using fluorine couplings. Also, people use things such as like proton-driven spin diffusion, where you basically, you know, you prepare one fluorine spin or one carbon spin in like a very high polarized spin state. You let this evolve, and you kind of measure how much of that spin is propagated to other spins in the system. However, this tends to decay quite quickly, and you have like, you know, kind of this you're dealing with like decay, like you're dealing with a diffusive process that doesn't leave much information. Okay, and so the idea here is that OTOCs allow you to get around this, because, you know, these are out of time autocorrelators came out of the strongly correlated physics community as a means of getting a signal out of an interacting system, right? So if I take, you know, my conventional measurement, which kind of is limited to short range distances, because these things are typically, you know, these things typically scale as the inverse cube of distance between 2 spins. If I use an OTOC, I can propagate information from one spin all the way down to a butterfly, and then play with, and then you know, like apply a perturbation in this butterfly spin, and then I can replay time, you know, go back in time, undo all of my evolution, and measure how much that perturbation affected my spin, and that gives me a time of flight of how I can go for, you know, how long it takes in spin information to propagate from one spin to the other. And it's a very strong signal, right? It's a strong signal in large systems. However, the challenge with this is that you only get a time of flight measurement, you don't actually get a distance measurement. And so the proposal for us is, and this is why we're interested in it, is that there may be quantum advantage in interpreting these OTOC signals and extracting data from the NMR experiment. Okay, so that's the proposal for the application. It's a little bit long-winded. I apologize for that. But we think that we do think that there is a quantum advantage to be found here. And actually, if you look at, we've done some toy examples of these dipolar spin systems, and definitely like inverting the OTOC evolution or modeling the OTOC evolution in these systems, it looks like it's going to be quite a challenge to do classically. Now, one thing that I think you might have picked up on is I talk about, in order to do an OTOC, you need to go backwards in time, right? You need to sandwich your butterfly operator by U and U dagger, right? And this is not something that you can necessarily do in a real physical system, right? Like going backwards in time is not like the experimentalists don't have a magic knob which just reverses time, or they would be doing things other than sitting in the lab. The trick is that we don't actually reverse time in an NMR spectrometer. Instead, we generate an approximate, like an effective Hamiltonian, that we can invert under a symmetry. Okay. And so this is like in the field of Hamiltonian engineering. If I was a smarter person, I would have put, there's a very good paper, there's a very good set of papers out of the Lucan group from Harvard that go through the details of how to do this. But the idea is that the one handle that I do have in an NMR spectrometer is that I can apply the same operation to all of my qubits, basically by applying a time-dependent magnetic field that just kind of like rotates all of my spins. Okay. So then what I can do is I can work in the Heisenberg picture. And, so then I can think, instead of me rotating my qubits, I'm rotating the terms of my Hamiltonian. So instead of me applying this rotation to the state, applying the rotation to the Hamiltonian, working in the interaction picture, I guess. And so, what you can think about here is to say, okay, well, here's my original Hamiltonian, right? This HC, where I've dropped this third term, this J coupling term, right? But here is my dipolar interaction. And something to note here is that if I apply, say, like a Y pulse or a pi pulse in the Y direction on all of my spins, that's basically doing an echo. That will start canceling out this on-site term if I do it fast enough, right? A pi pulse doesn't cancel out the dipolar term because it's quadratic, right? So if I apply a minus sign to every single one of my, so if I apply a pi pulse in the Y direction, that replaces Z with minus Z. I'm sorry, I don't know if this is don't think they teach this in everywhere, but yeah, but if I replace Z with minus Z, and I'm doing that for every Z, then obviously ZZ, it doesn't change. However, I can apply a pi over 2 pulse, and pi over 2 pulses will say switch between two of my Pauli operators. So a pi over 2 rotation in the Y direction will switch between ZZ and XX, and it will switch between XX and ZZ. And you can see now that I've got a different Hamiltonian, right? I can also like make the YY have the -2. And then because they have kind of like this nice balance condition where the sum of the coefficient in front of XX and YY and ZZ is equal to 0, I can use these types of rotations to generate any Hamiltonian that also satisfies this condition, okay? And so you can check down here that, this HC 1/6 times HC plus HC minus plus 1/3 times HY plus HY minus is what we call this double quantum Hamiltonian, which takes this Dij XIXJ minus YIYJ form. And if I sandwich this double quantum Hamiltonian by Z rotations on either side, or generate the sequence over here, you'll see that the Hamiltonian inverts, okay? And the reason why I'm taking this sum, right, the idea is that I'm applying these, if I apply these pulses fast enough, right, and I work in to lowest order in effective Hamiltonian theory, sorry, in average Hamiltonian theory, this will be the effective Hamiltonian that I work under. Okay. In the real experiment, we have a different pulse sequence just to try to like make this more accurate. It gets a different pulses for the carbon and the proton and 13 and the carbon 13 spins. I realize I'm almost completely out of time, so let me just skim over the actual results. So we studied two molecules in particular, two molecules in the data. These are two molecules where we had real real molecules were like they were put in an NMR spectrometer in Berkeley, and then we try to simulate them classically and on the quantum computer. For both molecules, I'm kind of like, both molecules are carbon-13 labeled. We use that as a measurement qubit. And for the butterfly spins, we use the blue circled spins up here. Okay. The first thing we did was toluene, which is a bit of a benchmark system. You can kind of see here, here's a picture of how the OTOC evolves, right? You start in the measurement qubit down here. You let that spin evolve up to the butterfly sites. You then apply a butterfly perturbation. You let this thing evolve, but it doesn't evolve back, but it doesn't completely evolve backwards because you've perturbed the system. You have the butterfly effect and you see something. If I don't apply the butterfly, then I'm doing what we call a low-Schmidt echo. And this decay here kind of gives you an idea of the experimental error in the system. This error is dominated by finite temperature fluctuations and some pulse miscalibrations. This error is actually dominated, by higher order corrections to the average Hamiltonian scheme that we were using, and by some pulse RF inhomogeneity, which I don't have time to get into. But we can build a pretty good classical simulation for this model, and we can actually feed this in, and we can play a learning experiment where I try to relearn a geometric parameter of the system. And you can see we do this quite well. We learn this. We can learn this like ortho meta hydrogen distance down to sub-angstrom precision. I'm actually kind of like down to picometer precision by fitting this cost function to the real experimental data. So that's good news. We can replicate this on the quantum device. Here, obviously, we pick up a little bit of extra data because the quantum circuits you have to run for this, they're not very many qubits, but they are very deep. Okay, and so we're talking about 600 to 700 gates to simulate this circuit. But still, we're able to, with some slightly worse error bars, we are able to replicate the learning algorithm. And then finally, just to finish up in the last 2 minutes, the second molecule that we were interested in learning was this. It's a dimethyl biphenyl. If I go back here, I can just show you this is the molecule up here. And this molecule has a nice feature. It was chosen for this purpose. It has this dihedral angle, which is like the angle between the two methyl planes. This angle is this bond is quite floppy, right? So this angle is quite hard to pin down, with just classical simulations. Molecular dynamics simulations will get this angle completely wrong. And so what we can try to do is we can try to use the OTOC experimental data to actually pin this angle down. Okay. Now, there are a lot of caveats to this. So for instance, you can't just, this molecule is this bond is so floppy that you don't just have a single angle to learn here. You have a distribution of the set of all angles to learn, right? And so we parameterized this. We basically built a model for these distributions. And then from each of these models, you can average over the Hamiltonians here to get, you kind of combine, your estimate of the distribution with some molecular dynamics simulations to get, and then you run this through a quantum computer or a very large classical simulation in order to get an estimate of the OTOC. And then you compare this with the NMR experiment, and you can produce another RMSE curve like this guy here. And we can try to learn the simulated angle. And one of the things that I'm particularly proud of here is that then we actually went and tested this after the fact with a more standard spectroscopic technique in NMR, which is this multiple quantum coherence, which is the green data. And we tested this technique, and we found that the data that it got was matched the predictions from the OTOC exactly. So we're pretty happy with this. I want to shout out to Alec White, Justin Vavaza, and Nick Rubin, who did all of the classical simulation of this, and Chongwei Zhang and Christian Beng, who took all of the experimental data. And with that, I believe I'm done with 10 seconds to go. So thank you. I'm sorry for not leaving enough time for questions. I'm happy to stay around for 5 minutes if you guys aren't going to get kicked out of your room to answer anything else.
So, does any questions from both sides? Actually, I guess the others are.
Maybe just a bit detail of this experiment. So did you set up a Hamiltonian on your quantum computer with like an unknown parameter? and you want to tune this parameter so that you match like existing experimental data like on the molecule level, like what is kind of the logistics of this experiment?
Yeah, that's a good question. I definitely like went over this way too fast because I ran out of time. So yeah, so what we do is we first have to build a model that's a single parameter model. Okay.
Yeah.
And so this is done via like a mixture of some clever molecular dynamics simulations to kind of what you're doing is so molecular dynamics simulations, you take like a classical force field for approximation for your molecule and just let it evolve in free space.
Sure.
And as it evolves, you kind of like, you get a slightly different Hamiltonian, like dipolar coupling Hamiltonian every single point in time. And so what you do is typically you would just because these rotations are so fast, they're much faster than the scale of the NMR experiment, you just average over those Hamiltonians. Okay, and that would give you the molecular dynamics predicted Hamiltonian, which I believe is somewhere up here. Then what we do is we reparameterize this. And the way you reparameterize this is you say, okay, we know molecular dynamics does a terrible job of predicting this dihedral angle, right? So it's going to predict a distribution of the dihedral angle that's entirely wrong. But if I fix a dihedral angle, it probably gets everything else correct. So we take those Hamiltonians, we bin them according to the dihedral angle. We take the molecules, we bin them according to the measured dihedral angle at every single frame in our molecular dynamics simulation. And then we take that, and that gives us kind of like a Hamiltonian as a function of dihedral angle. We then generate this set of distributions that you can see here, right? And these are estimates of, this is like the potential of mean force. So this is like the same thing as the free energy, right? And so if you take this distribution, if you take like e to the minus beta times h on this guy, that will give you a probability distribution of your dihedral angle. And so you can kind of integrate probability distribution times Hamiltonian, and this will give you kind of like, this is this combining of this P of phi and MD to give you a set of DIJs, okay? Once you have these DIJs, you have the Hamiltonian, and then you just put this through like the pulse sequence and the quantum simulator to actually once you get that Hamiltonian, then you can estimate the OTOC. So the quantum computers part is just take a DIJ matrix in and spit out an OTOC. Okay, and then there's an awful amount of physical pre-processing that has to be done in order to get these DIJs.
I see. So pre-processing is basically MD, like molecular dynamics.
Yes, exactly.
Angle to the molecule. I see.
Yeah, I mean, I don't know. Let's not say I get in trouble every time it's not. It was a bit. There was a lot more that went into it than just molecular dynamics. Mm-hmm. You have to be pretty careful with these systems that you actually you have to be pretty careful with your choice of force field. You have to be pretty careful with the reparameterization, etc., in order to get this P of phi model that actually works. I think anytime I say it's MD, then the chemists get a little bit upset at me. But the workhorse of this is the workhorse that we use right now is molecular dynamics. In a larger system, you would do some combination of, say, molecular dynamics, AlphaFold, and then probably clever model construction.
I see. Thank you.
I also have a question. So, will you do this type of experiments like OTOC or you learn something like that? They are organized by projective experiments.
Sorry, that was actually a bit hard to hear. You're asking whether we do projective measurements in the OTOC?
Yes. So it's like a big counting, and then you calculate the ratio between something or alternative probability. That's
a really good question. So in an experiment, so if I go back here, this is kind of if you're an NMR expert, this is kind of like the description of the experiment that might make a bit more sense. In NMR, the thing that you calculate isn't actually like the OTOC. It's the only thing you can ever measure is what they call the free induction decay, right? And the free induction decay is basically you're measuring the expectation value in Z of the mean magnetic moment of your molecule. And so what you need to do is you need to take this free induction decay and Fourier transform it, and you extract the peak that corresponds to the carbon-13. and that peak corresponds to like the back propagated magnetization. But this is entirely like, so NMR is an ensemble technique, and it is entirely an expectation value that you're measuring. You never actually do a projective measurement in the experiment. On the quantum computer, we can, but then obviously we just do the averaging.
I have a question. So I understand that this is a benchmark for the ability of OTA. And but right now, I think in these benchmark problems, the quantity that you're measuring are pretty much like some sort of a geometric quantity of a molecule. And is there some sense, or maybe in these experiment, or maybe in the future, that you can say something about why OTOP is the preferred thing to measure, so and that may be more sensitive, or I don't know, maybe better for characterizing certain things because it's difficult to calculate. So.
No, that's a really good question. That's a really good question, fair question. It's also the question we got from some of the referees. So the point is basically that you can you can show numerically for sure that if I make this molecule bigger and bigger and bigger and bigger and bigger, in the absence of any decoherence, I'll still get a signal from the OTOC, right? It doesn't matter how far apart my spins are split. As long as my system isn't decohering, and as long as there's like some coupling from spin A to spin B, you can do an OTOC and you'll get a signal at late times, right? And almost no other, like most other NMR techniques that work in the time domain or like work on these many-body systems, none of them have like this ability to kind of measure at really long distances. So actually, like measuring like distances in NMR, calculating distance restraints at like the 20 to 60 angstrom level, this is kind of like a pretty, we've been told that this is a pretty big deal for the field. So the downside, like definitely like the systems that we've studied here, like one of the downsides of this study is that these systems are quite small. You can definitely, if you should definitely be able to do like some kind of PDSD or some kind of reader experiment and actually see a signal from the carbon up to the hydrogens. Because it's a liquid crystal, it's kind of hard to check this, but we're actually working right now on trying to get some time order correlators in these systems to compare their measurements to. But yeah, and the other types of experiments that people would typically do on these systems is like real spectra. But spectroscopic measurements, so like multiple quantum coherence spectroscopy, tends to break down after about like 12 spins. Actually, I should note that like for this dimethyl biphenyl compound, we couldn't actually do MQC spectroscopy on the original compound because it had too many hydrogens. We had to instead deuterate a bunch of the methyl groups so that we could get a result. So yeah, so like basically the thing that we expect OTOCs to have an advantage in is measuring these long range distance restraints. We're working right now to try to like prove that theory, like kind of probably prove that in like a quantum computer science sense, and then also try to to demonstrate in a way that's more convincing to the NMR community. But like I would say, if there's an old paper that I wrote with Tommy Schuster back from 2023, I think, that looked at doing these OTOCs in a spin chain compared to time order correlators, and under some settings you can even see like an exponential improvement in the amount that you can learn from this.
Thank you.
Yeah, really good question. Thanks.
Okay, so if there's no any other question, let's thank the speaker again.
Yeah. Thanks everyone. Have a great day, and hope to see you in the March meeting maybe.
Sure. Thank you very much.
Ciao.
That's really all I need to have for the session.
Okay.